Welcome back to EasySpin Academy 2020. This is day 2 in session 11. In this session, we will revisit for the third time least squares fitting and talk about some of the more advanced features that are available with EasySpin's least squares fitting function called esfit. So first of all, let's try to simulate to cover two important use cases that we have not been able to cover so far. The first use cases is you want to couple several spin system parameters together. For example, you have two nuclei and you want to lock those two hyperfine couplings together in a fixed ratio. For example, you might know these values or this ratio from previous experiments or from density functional theory calculations. Another use case is if you want to fit experimental parameters, such as the temperature, the microwave phase, or field shift. We're going to look at these two use cases in turn. So first, let's couple some spin system parameters together for esfit. So you're going to this time generate some data. And I'm just going to copy some spin system code up here. We take a G value of 2. We're going to use 3 different protons classes. So we specify sys.nux, and we give a list of 3 times protons that are comma separated. And then we specify sys.n, which gives the number of equivalent protons for each of the 3 classes. So 2 of the first class, 3 of the second class, and 2 of the third class. So we have a total of 2 plus 3 plus 2, which makes 7 protons. Now we specify the hyperfine couplings, and these are isotropic hyperfine couplings just for simplicity. So 20 megahertz for the first proton class, 30 megahertz for the second, and 50 for the third. Now let's assume we have this fixed ratio of 1 to 1.5 and 2.5, and we'll try to use that information. First, we'll need to simulate the spectrum, so we'll just add a little bit of line width. We also add the experimental parameters, which is a microwave frequency and a field range. And then we'll simulate the spectrum. Let's do that here. I'll just copy paste that again. We'll simulate the spectrum using garlic, since we're only using isotropic hyperfine couplings, so this situation is in a fast limit regime. Now we're going to add some noise. And there's an EasySpin function for that, and that's called add noise. So this function is you need to supply it with the noiseless spectrum as the first input. Then as a second input, 100, this is the signal to noise ratio that should be achieved. And then the third one is the nature of the noise you want to add. And add noise supports uniform distributed noise, Gaussian noise, and also 1 over f noise, which if you specify f, it uses the 1 over f noise. And finally, we plot the spectrum to see how mock data looks like we want to fit. Here it is. We have a lot of lines, and we've got some noise in the baseline. Now, the first thing we're going to do, we try to fit the hyperfine values individually, right? Fit.a equals 5, 8, 12. We're going to specify a variation structure. So this basically tells esfit that it can vary these 3 hyperfine couplings by plus minus 5, plus minus 8, and plus minus 12 respectively. And we're just going to call, as before, esfit using the garlic function. And don't forget to include the at symbol to make this a function handle. And then the experimental spectrum, the spin system, the parameter variation information, and the experiment. Now we press Control Enter. And what did I do wrong? Sysvariexp. It did crash on me this time. There we go. Okay. So now you see the esfit graphical user interface, and we are again in a situation with a lot of features in a spectrum. This is going to be not easy to fit right out of the box, and you can see that, appreciate that pretty quickly. Well, you know, we're kind of lucky because we have a really good starting points, as you can see, and so the fit does work very nicely. we could start, let's assume we do not have good starting points. So let's say our starting points are actually sys.a, they're really off. Let's say 16, 36, and 47 or 46. And run this again. And you will see it's much more difficult. Right? But, you know, it is also quite successful here. Now you might want to improve this fitting situation by kind of locking these hyperfine values together in this ratio that we know. So ratio 1 to 1.5 and 2.5. So we actually only want to fit one parameter, and then use one hyperfine, and then calculate the other two hyperfines based on that hyperfine. So that we end up fitting one parameter instead of three, and that's always advantageous. In order to do that, let's remove vary. We need to write our own custom simulation function, and that is going to replace garlic. And in this function, we're going to lock those or couple those parameters together. So here is how to do it. At the end of your script, at the bottom, you can write function, and then you have to specify an output, what the function should output, and it should output the simulated spectrum. And then you can give it whatever name you want. Let's call it my sim function. And this function has to take the same inputs as garlic does. So a spin system, an experiment, and an option input. And if you finish the function with an end keyword. Okay. Now we're going to use how to make up this parameter we want to fit, right? It's not any of these parameters, but it's a new parameter. It's a user-defined parameter. And you can just add any parameter you want to your spin system. If it's not matching anything that EasySpin understands, EasySpin will just ignore it. And what I like to typically do when I do this, I preface my own parameters with my. So in this case, I want to have my A in there, and it's going to be going the first A. So we might want to start it out at 20, and we're going to vary that, my A, by ±5. And these are, as always, megahertz. So now we've specified a new parameter that EasySpin didn't know about, but we have to include it convert it to EasySpin input so it gets included in the simulation. That's what we do in this function here. So we take the input, sys.ma, my A, and then basically generate sys.a from it by multiplying it with 1, 1.5, and 2.5. This takes this single number, multiplies it with this vector of 1, 1.5, and 2.5, and basically makes a 3-element hyperfine array as is expected for the simulation function. And then you just call the simulation function, in our case garlic, with this now the system, exp, and opt. Right? So what have we done here? We've introduced a new parameter, and we've written a new function that kind of takes that new parameter and uses it to construct some spin system parameters that EasySpin understands. And that is the general procedure if you want to constrain spin system parameters with your own fit. The last thing we need to do, of course, we need to tell esfit to not use garlic directly, but this small kind of wrapper function around garlic. So we say, instead of at garlic, we say at my sim fun. Okay. And that should just fire up a simulation with only one fitting parameter called my A. So let's do that. We can click Run Section or Control Enter. And here is the fitting. And you can see there's only one parameter now, and everything else is exactly the same. On top, it tells you that the function that's being called is mySimFun. That is the function that we just defined here. And now we can press Start. And you can see the fit is much faster, because now all the hyperfines are linked together, so the whole spectrum expands and shrinks at once. So this is just a made-up situation that kind of represents this use case that you want to couple different spin Hamiltonian parameters together. All right, that was the first example. Let's do a second example. of coupling spin system parameters together. When you have high spin systems, that often, and your zero field splitting is very large, then very often your spectrum does not depend on the actual zero field splitting, but only on the ratio of two parameters, E over D. And so let's make an example for that. For example, large zero field splitting spectrum depends on E over D, not on D and A. So zero field splittings are parameterized by these two parameters, D and E. But if D is extremely large, then D doesn't really matter anymore. And only E, or even better, the ratio E over D matters. So let's simulate a spectrum. Let's make a spin 3/2 system and add a really large D value with 100 gigahertz and a 0.1 value for E over D. So this is basically D and E. It's in megahertz. And let's add some broadening, like 5 millitesla. I'm going to copy the experimental parameters from my script. So 9.5 gigahertz, a large sweep range, and it's 10 Kelvin, low temperatures. Now we're going to also use, we have to use more orientations to get a smooth simulations. And we also use a new feature where we can specify which of the many transitions in a high spin system we actually want to simulate. And I'm going to just limit myself to the transition between level 1 and level 2. And the levels in EasySpin are always numbered from the lowest energy all the way up to the highest energy. Okay, now we can simulate the spectrum with peppers, a rigid limit powder spectrum, and we can also add some noise to make the fitting non-trivial. Again, signal to noise of 100 with a 1/f noise. And then let's plot the spectrum and see what we get. Control Enter. It's busy, and voila. Here you can see this is now a spin 3/2 spectrum with a really large zero field splitting that's much larger than the microwave quantum. So it's 100 gigahertz zero field splitting versus 10 gigahertz microwave quantum. And what you see, it kind of looks like an effective spin 1/2 system with just 3 lines. It looks pretty rhombic. Okay, now if I change D, for example, I change the D from 100 to 200 and press Control Enter and run it again, we see we get the same spectrum. The noise has changed because we generated a new noise sample, but the spectrum is exactly the same, showing that D is irrelevant, right? So we really don't have to fit D. We can change E, but that is also going to be a very large number. The ratio E over D is nice because it's usually constrained to be between 0 and 0.33. So that's the easiest parameter to fit. So in order to do that, all we need to do is, now that we have the spectrum, we introduce a new parameter. Let's call it my E over D. And let's start out with an initial value of 0.15. And then we have the vary structure with my E over D equal to, let's say, plus minus 15 or 14, not to hit 0. Then we need to call esfit with a simulation function. We still have to write my simfun. We supply the spectrum, the system, information about the parameter variations, and the experiment. And finally, we'll need to write that function here. This is a function. I'm going to call it my sim function. It will take a system, an experiment, and options. And it will return a simulated spectrum. And what I do here is I say sys.d equals 100 gigahertz times 1, and then sys.my E over D. I'm just fitting that in there. And then we're ready to actually simulate the spectrum by saying spec equals pepper sys, x, opt, end. That's it. So with these few lines, you've written a little custom fitting function that's just a very thin wrap around pepper. It helps you constrain parameters, or introduce new parameters that are more suitable to your fit. Okay, let's run it. And it fires up, and you see the only parameter that's available here is my E over D. And we can run a simulation, and you can see that the simulation works nicely. It already has a really good fit. It's getting a little closer, and we can stop it now. If you look closely, you can see there's some wiggles here, and we also see some extra absorptions here. This is because we forgot to feed in the options we've specified, which means more knots and just a limited, just one single transition. Let's run it again and see if these wiggles in the simulation go away. It is slower now because we are using more orientations in order to get a smoother spectrum. So you can see it takes like 2 seconds for every step to complete. And it keeps going. As you can see, even though Nelder meets simplex often finds the minimum, it's still stepping around the minimum for a little bit, just to make sure it didn't get caught in a local, very local minimum. So Nelder meets simplex is a little robust against shallow local minima. It's able to walk out of them. But now it seems like we're converging, and you can see the currently best fit value here is 0.1. which is basically identical to the number we initially assumed for generating our mock spectrum here. Okay, so this is the first use case for using these custom functions, which is linking 2 different spin system parameters together, 2 or more. And the way to do it, again, to summarize, you define your own parameter, you write your own function that wraps around pepper or garlic or chili, and then you feed that function into esfit. The second use case was if you want to fit experimental parameters. You know, sometimes you don't know everything about the experimental setup. You might have a spectrometer where the magnetic field is not really well calibrated. And so you might want to calibrate that field, and you have a sample in there where you know the G value, and you would just want to fit the field shift you have to apply to convert your nominal field to the actual field value. Another one is, microwave phase. We can adjust when we phase, when we tune the spectrometer, we typically adjust the phase to within a degree or 2. But if you do very, very careful line shape analysis, those few degrees offset will distort your line just minimally, and you might want to correct for that. So you could fit the microwave phase. And the one thing I want to show you today here is how to fit the temperature. You might have a low temperature setup, and on your temperature controller, the temperature is set to 10 Kelvin, but you actually don't know what the temperature at your sample really is. If you happen to have a high spin system in there where the EPR spectrum is sensitive to the temperature, you could then use esfit to actually extract the sample temperature from the spectrum. Let's see how that goes. So we're gonna clear CLC and CLF to start from a clean slate. And I'm gonna use this time we're gonna use a triplet system with a large 10 gigahertz zero field splitting and a fairly large line width. And we're gonna simulate, this time we're gonna go to W band. So we're gonna use a frequency of 95 gigahertz. And also, so we have to sweep from 2,800 millitesla to 4,000 millitesla to just capture the entire spectrum. And we're going to do this at low temperature, 4 Kelvin. Now, I'm going to simulate the spectrum with pepper. So again, assuming solid state, frozen solution, or powder. We add some noise, and we're going to plot the spectrum. Voila. The noise is a little much, so let's actually reduce the noise a little bit to see what's going on. We're seeing the 4 features we expect for a triplet, and they have very different intensities. So this one and this one have different intensities because of the low temperature. If I change the sign of D, make it negative, and I simulate this again, you will see that these 2 intensities are swapped. So the spectrum is sensitive to the sign of the D value. Also, if I change the temperature, let's say I go from 4 Kelvin to 40 Kelvin, I can see that these two central features become more equal in intensity. So the spectrum is also sensitive to temperature. Okay, let's go back to 4 Kelvin. And now let's pretend we don't know this temperature that we simulated, and we want to now extract it from this spectrum. I think we should reduce the signal to noise a bit again to this. All right, so now the temperature is an experiment parameter, right? So it goes into the second input structure for Pepper. And esfit does not look in there for any fit parameters. So what we need to do, we have to make our own temperature parameter and feed it in through the spin system side, and then have a wrapper function that copies it over from the spin system to the experiment structure. Okay, so first let's introduce our own parameter, sys.mytemp. And let's start with 5 Kelvin. And we let it vary my temp by plus minus 4. Okay. Now we're gonna call esfit again. We're gonna write a function again. We're gonna feed it the data, spectrum, the system, what can be varied, and the experiment. And so let's write this function again. We will have to return a spectrum, which is probably better to call this spec_exp to make sure it's a spectrum. So my sim_fun here, it takes system, system, exp and opt, and let me regenerate this data here and feed the extra experimental data. So what do we have to do in this now custom simulation function? Well, the situation is the following. In the spin system, we have this user parameter called mytemp. EasySpin completely ignores that. But we want it actually to specify the experiment temperature. All right, so all we need to do is set the experiment temperature to this custom parameter value that's being fed in. And then finally, just say spec equals pepper sys_exp opt. Okay, so basically esfit, when the fitting algorithm is running, for every iteration it will call this function instead of pepper directly, right? And so this function, it kind of looks the same as pepper from the esfit's point of view, right? It just takes these 3 inputs and it returns a simulated spectrum. But internally, it just does one little extra thing. It just copies one parameter over from the spin system to the experiment. All right, I think we can run this with Control Enter. This brings up the interface, and we can click Start and see what it does. Oh, and it works great. You know, single parameter fits on mock spectra always work great. I mean, as soon as you have more than one unknown parameter and your experiment is actually from a real sample, things are not as trivial. But we can't do that in this brief workshop. It would take too long. But anyway, this shows you the basic idea of how you can write a custom simulation function that allows you to fit an experiment. This is kind of all I wanted to show you about custom simulation functions. You can also use them for a variety of other purposes beyond just coupling spin system parameters or dealing with experiment parameters. You could, for example, mask out certain regions of a spectrum, or you could combine multiple spectra together and fit them at the same time. All these things are possible by using these custom functions, but the code will get a little more complicated. This brings me to the end of this session, and now head over to documentation. Let's head over to the documentation first and see where information about these custom functions is findable. So there's the least squares fitting user guide. If you go there, there is one section at the bottom that talks about user-defined simulation functions. That is a really good starting point. It has an examples, a constraint between systems, and varying non-spin system parameters, and also about globally fitting multiple spectra. So go there for an initial orientation of how this works. Okay, let's go back to MATLAB. And I think Stefan Pribitzer, who is who is running all the tech behind the scenes here, has prepared a little poll on Slido for you that we ask you to fill out. And the poll asks you to tell us what you want me to cover tomorrow in these flexible sessions where we haven't scheduled topics yet. We'll try to accommodate as much as we can. So please give us feedback by the end of happy hour today, so I have time enough to prepare something for tomorrow. You head over Slido and let's see if I can figure this out. There should be a poll, and what you should enter is one word, because we're going to generate a word cloud, and based on that word cloud, we will pick the topic. You could, if you have two words, just put a hyphen in between, and it will still show up. Okay. So please run this poll now. I hope Stefan has activated it, and please give us feedback. Okay, that brings us to the end of this session number 11. We are about 13 minutes out from the next session. So take a break or look at the documentation or run the script. The next session will be the last one on a specific topic today, and it's going to be on basic pulse CPR simulations. So see you in about 13 minutes.